Good morning. In the last class, we learned how to draw Lewis structures for molecular compounds and polyatomic ions. Well, Lewis structures are useful for a lot of different things, and they provide a great starting point to understand the structure of molecules. One key thing that's missing, right, is a message of or an idea of three-dimensional shape. So Lewis structure gives us a two-dimensional structure of a molecule, which of course is not how molecules exist in reality, right? We have to understand how they exist in three dimensions. And so we can combine or add on a separate theory to Lewis theory to get this three-dimensional component. And so this is what's known as valence shell electron pair repulsion, or VSEPR theory. And it can be used to predict the shapes of molecules. So this VSEPR theory is based on the idea that electron groups, so these are groups of electrons that are surrounding an atom. So these groups can be lone pairs, right? They could be various bonds, so single, double, or triple bonds. And they repel each other. So if we remember back, electrons are all negatively charged. So these different groups of electrons would like to space themselves out as far as possible. So what we want to imagine, right, is that the center of our molecule, the central atom, is a sphere, right? And the groups will want to space themselves around the sphere, so in 360 degrees, to get as far away as possible. So of course, how far they can get apart is going to depend on how many groups they are. So the first key point here is we need to determine how many electron groups there are around the central atom. And this will determine the geometry of our molecule. So if we start by looking at one of the structures we drew last time, so carbon dioxide, or CO2. So when we drew the Lewis structure, it looked something like this, right? Where we had our carbon in the center and the two oxygens connected by two double bonds. Now, if we look at these groups, we can see that we have 1, 2 electron groups around carbon. So one key thing to understand here is that a double bond, even though it's 4 electrons, right, is still one group, because this double bond is tied together by its bond to oxygen. They're going to exist as a group of electrons. So it doesn't matter what kind of bond it is, a single, double, or triple, it's just going to be one group. And a lone pair would also be one group. So we have two groups here. So if we have two groups around a sphere, those groups are going to want to be on opposite sides, or in other words, they're going to be 180 degrees apart. So we end up with these two electron groups being separated by 180 degrees. This gives us what we know as linear geometry. So as we go through this, we're going to give these names, right? We're going to look at the different patterns of electron groups, and these are going to give us the various three-dimensional geometries that molecules can have. So the first one is if we have two electron groups around a central atom, that's going to give us linear geometry. If we go to another molecule, this is H2CO, right? Lewis structure looks like this. And if we notice, we have 1, 2, 3 electron groups around our central atom. So we have 2 single bonds and a double bond. So if we think again about 360 degrees, we can get 3 groups separated by 120 degrees around that central atom. So we'll have bond angles of 120, and this is called trigonal planar geometry. So trigonal because of the triangle shape, and planar because the molecule is flat, right? They could be 360 degree sphere, but they're going to be in the same plane. So 3 electron groups, trigonal planar. Now, there are other options for 3 electron groups, and we'll talk about that in a second. Now, of course, in all of these molecules, the angles are approximate, right? Once you get beyond 180 degrees, where there are just two of them, then when we get to 3 and to 4 groups, these angles become approximate because they're going to differ based on what the exact atoms are and the different constraints of that molecule. So the best we can do is sort of approximate those angles to, say, 120 or other angles as we go into different numbers of electron groups. So in reality, if we look at that molecule, the bond angle is actually 116 for the two of them and 122 for the third one. And this has to do with the fact that these are different atoms bonding around the central atom. We have the oxygen and we have the two hydrogens, and those groups will repel each other a little bit differently. But for our purposes, we just need to understand that the bond angles are going to be approximately 120 if we have 3 bonds around a central atom. Now, if we keep moving up to 4 bonds, so if a molecule has 4 electron groups around its central atom, we call that tetrahedral geometry. And the bond angles, turns out the maximum they can get is to be about 109.5 degrees. So it looks something like this, where we have our central carbon here, and these things are spread out. So we have one pointing straight up, we have the 3 on the bottom like a tripod, 2 pointing slightly back at angles, and then 1 pointing out toward it. So if we think about standing something on a tripod with something pointing up, those angles between them would be 109.5 degrees. And so we can see here, right, the Lewis structure is useful, but it doesn't give us the whole picture, right? It gives us a 2-dimensional flat geometry, and in reality, not all of these molecules are flat. A lot of them are linear, trigonal, planar, but many of these have significant 3-dimensional shape. So when these groups repel each other, they give us this tetrahedral shape. Now, when we write this, we may often write it like this. There's nothing wrong with that. That's how we will easily show it. This is how books will often show it. Now, I'm not going to require you to write things with perspective, right? Unfortunately, this isn't an art class. If we took some time, we could all learn some techniques that we could use to display this sort of perspective, but it's not really necessary. At this point, we just want to understand conceptually what the real shape of these molecules are if they have a certain number of electron groups. Now, everything that we've dealt with so far has to do with everything being bonds, right? We had 2 bonds in CO2, we had 3 bonds in H2CO, we had 4 bonds in CH4. But as we saw in our Lewis structure, sometimes the groups around the central atom are not just bonds, right? We have lone pairs, like in ammonia here. Well, this is still 4 electron groups, right? We have 1, 2, 3, 4, right? But one of them happens to be a lone pair. So the basic shape is still a tetrahedral. But we distinguish it in terms of the geometry. We have a special name for it because what we're really naming is the shape of the atoms, right? That lone pair is there, but it's not part of the shape. It influences what the shape of the other atoms are going to be or how far the other atoms will be apart from each other, but it's not really part of the shape of the molecule. So we call this geometry trigonal pyramid, right? It looks simply like a trigonal pyramid, right? It looks like a tripod where the central atom is the top and the three legs are separated like a tripod. And these angles are going to be, again, approximately 109.5. But what we can say is that this angle is going to be somewhat less than 109.5 degrees. Now, the reason it's going to be less, right, is because the lone pair has more repulsive power. Because it's not part of a bond, it has the freedom to sort of push out a little further, and it's going to shove these hydrogens further away, making these angles smaller than what they would be if we had 4 actual bonds here. All right, so let's look at one more geometry, and that is water. So this is another example of something that actually has 4 electron groups. 1, 2, 3, 4. But unlike the last two, where we had CH4, it had 4 bonds, and we called that tetrahedral, and ammonia, which had 3 bonds and 1 lone pair, we called that trigonal pyramidal. If we have 2 bonds and 2 lone pairs, it still, again, has a tetrahedral shape, meaning our bond angles are going to be approximately 109.5, but the actual molecular geometry, the shape of the atoms, is simply called bent geometry. So we have 2 lone pairs, 2 bonds, we're going to call that bent geometry, and again, the angles, the best that we can really say again, is that they're going to be less than 109.5 degrees. And based on the actual atoms, we'll determine that exact angle. So if we summarize here, we look at our whole possibility of geometries. So we've seen most of these. So the first one is we have 2 electron groups, 2 bonds, right? It's going to be linear. That's really the only possibility with 2 electron groups. If we have 3 electron groups, we could either have 3 bonds, like we saw, and that's going to give us a trigonal planar geometry with 120 degree bond angles. But if we have 2 groups and 1 lone pair, it's still a basic trigonal planar shape, but we call it, again, a bent. So we'll see as there's 2 versions of bent, one with 3 electron groups and one with 4 that we just saw with water. The difference being is that in this version of bent, the angles are going to be approximately 120 degrees. If we have 4 electron groups, there's the 3 possibilities that we saw. 4 bonds gives us tetrahedral geometry. 3 bonds with 1 lone pair. We have a basic tetrahedral shape, but we call it trigonal pyramidal. And if we have 2 bonds and 2 lone pairs, again, we have the same basic shape, but we call it bent. And so in all of these cases, the bond angles are 109.5, or with these ones with lone pairs, they're going to be less than 109.5. Now, while we have this table to learn from, for our exam, we will, of course, need to memorize these geometries. So what that essentially entails is you're going to be able to want to look at a Lewis structure here, and based on the number of electron groups you identify in this Lewis structure, you're going to want to be able to assign the molecular geometry, that's the important one, and the bond angles. So if we have a basic process for predicting the 3-dimensional shape, we of course going to need to draw a Lewis structure. Everything is based on that Lewis structure. We're going to determine the number of electron groups by counting around our central atom. We're going to, based on how many of those are bonding and lone pairs, we're going to determine the actual molecular geometry. and bond angles based on the information in the table 10.1 that we just talked about. But again, for the homework, it's great, refer to the table, but for the exam, we will need to memorize the information in that table, at least being able to the names of the geometries and the appropriate bond angles for those. Okay, I want to close out this section by doing just a couple examples. So the first one here is NO3-, the polyatomic ion nitrate that we did last time. We drew the Lewis structure last time. We came up with this Lewis structure. So what I want to do here is come up with the geometry. So once we have Lewis structure, remember our second step here is to count up the number of electron groups. So for this case, right, we have 1, 2, 3 electron groups. So we have 3 electron groups. And referring to our table, we see that if we have 3 electron groups, we have 2 choices, right? If they're all bonds, it's going to be a trigonal planar. Right? If we have 2 bonds and 1 lone pair, right, it's going to be a trigonal planar shape, but an actual bent geometry. So in this case, all 3 of them are bonds. All bonds. So our molecular geometry would equal trigonal planar, and our bond angles would equal 120 degrees. And that's the basic idea. So let's do one more, but this time we're going to go through the whole process. So this will give us a little bit extra review on Lewis structures. So we have SeO2. So first thing is we have to get a Lewis structure. So we have to lay out our basic skeletal shape. So we're going to put the Se in the middle, right, surrounded by the oxygens to give us our basic structure. Then we're going to count up the electrons. So for the electrons, we have 6 for the selenium, plus 6 for the 2 oxygens, giving me a total of 18 electrons. Remember, the first thing we do is we put in our bonds. So that used up 4 of my 18, remain 14 remaining. So if I look at my oxygens, turns out the oxygens still need 6 more, right? It has 2. We need 6 more here. So we can put those in. So it takes 6 to do this one, 6 to do this one. So that's a total of 12. So I have 2 more left. So I move to my central atom, and I can see here that it has 2, 4, so it needs 4 more. Now, unfortunately, I only have 2. So I can use those 2, but then I'm out. So if we remember from structure like NO3- that we did over here, or other structures, if we don't have enough electrons to give everything an octet, that's when we have to make a multiple bond. So we need to do that once because we need 2 more electrons. So picking from either side here, we can move one of these pairs in here to make a double bond. So our actual structure comes out looking something like that. So now we have our structure, 18 electrons. We have our Lewis structure. So if we move on to our geometry part, so we have 1, 2, 3 electron groups, right? So the single bond, a double bond, and a lone pair. So we have 3 electron groups. If we look at those, in this case, they're not all bonds, right? We have 2 bonds and 1 lone pair. So referencing our table and eventually remembering, right, if I have 3 groups, it's going to give me a generally trigonal planar shape. But when one of those is a lone pair, we call that molecular geometry bent. And our bond angles here are going to be less than 120 degrees. Again, we can't say exactly, but the basic angle is 120 with 3 electron groups, so when we have lone pairs, we know it's going to be less than. So this wraps up what I want to talk about for molecular geometry. So another reminder that there is the activity out there, the assignment that is due next Thursday on the 2nd, that will take you through several practice structures where you can do the Lewis structures, do the geometries, and you can be working on that, as well as the Chapter 10 homework, which is due on the 3rd. And both of these will give you extra practice in Lewis structure and assigning the geometries. Now, for that assignment, don't forget to be working on that. That is an assignment that is to be turned in. So make sure to be checking Talon, check the calendar. Again, that assignment can be found in the Chapter 10 section on the Talon course contact. Have a great day. Thanks.